students, good morning. Today we'll discuss about normalization of wave function and orthogonality of wave function. Okay. See, the Schrodinger wave equation is a homogeneous differential equation whose solution gives a value of psi. Okay. But psi, if it is multiplied by a constant factor, then also it should give the same differential equation. Okay. So now it is necessary to find some conditions which will give or which will indicate which constant factor is to be used. Okay, say as the electron must be found somewhere in the vicinity of the say nucleus, and say that is the probability of finding the electron in the whole of the space considered in a particular problem as unity. Okay, and this may be represented by, say, here it is integral of, say, mod psi square, mod of psi square into d tau is equal to 1, where the tau stands for volume of the whole space, and this integral determines what constant of psi must be, what constant must be multiplied with the psi for the solution of a particular problem. Okay, so this will give the that constant with which one can say multiply the psi to get the say a solution for a particular problem. So this constant is nothing but, or it is known as normalization constant. An eigenfunction which has been completely evaluated in this way is said to be, it has been normalized. Okay, so the amplitude in the wave function is determined by using this normalization condition. So for psi to represent a wave packet, that means a group of waves, the above conditions see for normalization should be satisfied. See, the numerical coefficient of psi or the amplitude factor should be independent of time, because Schrodinger wave equation is independent of time. Okay, yes, so this is about the normalization. So the next one is orthogonality of wave function. Suppose, say, consider two wave functions as, say, psi p and psi q, so which corresponds to two values of ep and eq, is it? Say if these wave functions are separate solutions of Schrodinger wave equation, then say integral of psi p into psi q d tau should be 0 or it equal to 0. That means the wave functions psi p and psi q are said to be orthogonal. Okay, it is said to be orthogonal. So when the two wave functions which are represented as psi p and psi q, in which on putting this one in the Schrodinger wave equation, on solving we'll get EP and EQ. EQ means what? It is the total energy of the electron. Okay, at P, that means at psi p, and similarly total energy of electron by putting the psi q value, is it? And when this, the product, when it is integrated with respect to say dot tau, it is equal to 0, then they are said to be, then these two are said to be orthogonal, and that can be proved in one direction, say in the direction of x direction. Okay, so now for in the x direction, see, by putting that value, by taking only the x coordinates, see the equation, Schrodinger wave equation can be written like this. See, delta square psi by delta x square plus 8 pi square m by h square ep minus bp into psi q equal to 0. Or another equation, say number it as 1, and by putting the q, say the same equation is written, it's name it as 2. So now multiply the equation 1 by psi q and the equation 2 by psi p and subtract one from the another. On simplification you get, say, 8 pi square by h square ep minus eq. So integral from minus infinity to plus infinity psi p psi q dx is equal to 0. But since EP is not equal to EQ, say the integration of this thing is equal to 0, that it indicates that. That means integration with respect to x over the whole space from minus infinity to plus infinity, since psi and v are 0 at infinity, psi and say v, that is potential energy and wave function at infinity, it is 0, is it? And thereby the first term vanishes. So in this case, the first term, when you subtract this equation from this equation, the first term, what you are getting, the first term, so this term minus the second one will be 0. Okay, and the second term regarding this one, okay, this term minus this term, so on simplification it gives, say, this equation. Okay, and now finally it indicates that it is possible to make a linear combination of orthogonal function. Okay, thank you.